Hello. Good evening. How are we all? My name is hopefully somewhere here. There we go. So, my name is Leif Beaton. I work for NGINX. Apologies for talking to you in English. In the week or so since I learned I was coming here, I didn't have time to pick up French. I picked up 3 things. Oui, non, and je pense donc je suis. So, yeah. Thank you. Was a Frenchman that said that, right? Anyways, I'm here to talk to you about microservices. Specifically, the big shift going from monolithic architectures towards a more microservices-oriented architecture. We're going to talk about some networking problems that ensue as part of that, and some architectures that possibly can solve those issues. So let's talk about the big shift. First, monoliths. Big, dangerous, difficult to maintain. Kilometers and kilometers of code. Any minor change inevitably ensues a lot of testing of the entire monolith, not just a small section that was changed. Any external components are tightly coupled with the monolith. The data travels through the monolithic application by virtue of function calls. Monoliths are considered evil, and to some degree I would agree, but they did their job in the time where they were supposed to do it. Luckily, that time is over. Microservices is a much more sensible approach to large-scale applications, in the sense that we can scale out an application both horizontally and vertically. We can make bug fixes, we can add features without having to test an entire monolithic application, without having to test 2 million lines of code. We can look at 1,000 lines of code, 10,000 lines of code. Now, the idea behind microservices is that we spread out our monolith into small defined services that has a specific function, does a small task of a bigger picture. So, we love microservices. We have always loved microservices. We've been working tightly with microservices for years now, and for as long as I can remember, if you go and have a look at Docker Hub, the most downloaded image would be NGINX, and we hope to stay there just for reference, so go download. Let's talk about the networking problem. When you have microservices, containerized environments, dynamic in nature, you don't necessarily know how many replicas you have of a service, or for that matter, on what node the service is running. So how are you going to talk to it? How are you going to send traffic to it? We need some kind of service discovery model so we can define where is the service I need to talk to solve this problem. We need load balancing, not only the clever layer 7 routing to send traffic to the individual services and so on and so forth, but we also need to be able to load balance between the replicas of a specific service. In this case, shopping, because we all like to do that, right? Finally, we need some way to communicate fast and secure. Security is a problem in microservices in a lot of instances. It typically shakes its head when we talk about companies that have some kind of compliancy situation. Think pharma, healthcare, banking, gaming for that matter. Anything that deals with finance, they need to secure their communication. But in microservices, you often find yourself in a situation where you have microservices applications running in a multi-tenancy situation. The thing about microservices is, we talked about the monolith sending its data throughout the application on the back of function calls. That's not the case in microservices. Internally in the service, perhaps, yes. But between the microservices, it happens as network traffic. And that, unencrypted, is plain text. That has some security implications we'll look at in a moment. So, what's the solution to these problems? Well, we need a proper service discovery model, we need robust load balancing, and we need fast encryption. How do we deal with this? We're going to look at some architectures that will touch upon this. We have what we call the NGINX Microservice reference architecture. It's a rather large document that was written by Chris Stetson, one of our upper echelons. It deals with a lot of things, but chief amongst them are 3 reference models. The first of them is the proxy model. When you look at the proxy model, it looks very, very familiar. It looks pretty much how a model with a monolith behind it would look. Do you agree? That's the truth. There is a perimeter NGINX instance doing the clever layer 7 routing and also load balancing towards the microservices that sits behind it. It improves upon a direct communication model in the sense that we can do SSL termination there, as well as do actual DNS service discovery. So the NGINX instance itself can discover where new replicas of each service pops up and introduce them to the load balancing pool. Secondly, we have the router mesh model. In this model, we keep the perimeter NGINX, but we put a routing NGINX in the middle of the microservices architecture as well. The reason for this is, in the previous model, this fella here, any communication between the services happen on the basis on the services handling that themselves. What that means is, when pages needs to talk to service 1, it will typically do a DNS round robin, and that's it. It's not more complicated than that. First request goes to service 1 A, service 1 B, service 1 C, etc. And that becomes problematic, and we'll see why in a moment. In this model, that's no longer true. In this model, you have a more robust load balancing engine sitting in the middle. It will take care of routing. It will take care of all the communication between the services. And we've moved SSL termination a level closer to the containers as well. Finally, ooh, wow. Sorry. Finally, there's the fabric model, in which case there's a routing engine sitting on each and every container. That may seem counterintuitive from a microservices perspective, but once you take into account that our routing engine, NGINX, is 3 megabytes in footprint, it makes sense again. The advantage of this particular model is the communication between each and every service can now be secured without the ludicrous overhead of encrypting it. I wonder if it's the next slide. Let me have a look here. We'll get there. There we are. Sorry. The advantage of that is when in a traditional model without the routing engine on each service, if you want to secure that traffic, there's a minimum of 7, more typically 9 requests between the services just to establish a secure communication tunnel. Once that communication has happened, and more often than not, a communication between services is less than 2 kilobytes in size, that secure tunnel is dropped, and a new one is created for the next one. So, yeah, let's stay there for a sec. That means, with a minimum of 9 requests before we have even done anything, if your latency is 5 to 10 milliseconds, you're looking at 50 to 100 milliseconds latency before you start your first communication. And that's per communication between the services. So, here's the normal process of communication Never mind clever routing and service discovery models and so on and so forth. Normally, first you have the DNS interface of the service registry, be that Kubernetes, console, etcd, zookeeper, swarm for that matter. It will report back to whatever needs to communicate with a stack of IP addresses, and in a containerized environment, also port numbers. Then it will start the, what's it called, the SYN-ACK process for securing a tunnel between itself and whatever it needs to talk to. Now, in the fabric model we were talking about, it's slightly different. We do the same with finding out where every service is and where every replica of every service is, but when it comes to the intercommunication, we establish the tunnel and we keep it open. So all subsequent communications will go over an established tunnel and not having to do the 100 millisecond latency all over again. So yeah, we've already covered this bit. Sorry. Yeah, when it comes to the load balancing between services, that's also a very important feature. Round robin itself isn't good enough. That's been established. So people started using least connections. Least connections was better. It was faster, more efficient, but still not good enough, because if I have a service over there with 1,000 connections that's very light, and I have a service over there with 1,000 connections that's very heavy, by virtue of connection count, they're doing the same work, but in reality, not so much. So we came up with a new load balancing strategy called least time, which looks at the connection count, but also the response time of each system. That's a vast improvement, but on its own, that's not good enough either, because you need an application health check system for that to be functional. And the reason for that is it's perhaps not immediately logical, but when you start looking at it in detail, it becomes clear. The fastest responding system in your stack is going to be the failing one. It's much faster to send back an error message than actually doing work and sending back a result. So on the basis of least time without health checks, you're just going to be hammering the failing system all the time, getting error messages back. So that's food for thought. Yeah. So yeah, we've already covered this. Applications in microservices architecture do generate thousands of connections. Research indicate that the average communication between services is less than 2 kilobytes, and they happen thousands and thousands of times every second. Each SSL negotiation, it says here 9 steps. That is typically true, but it's never less than 7 steps. So that's 7 messages going back and forth. So we solve that by keeping the SSL connection alive. Now, we mentioned active health checks and a circuit breaker design, if you will. We do cover that. In a lot of systems, you'll find that the health check system, the health check bit or component of it, is essentially looking at, am I getting a response from this service or not? If I'm not getting a response, we consider that an unhealthy system, and we take it out of the pool. If I'm getting a response, it's healthy. Is HTTP 404 healthy? 500, 503? Not so much. These are unhealthy systems. They should be taken out of commission in the pool, but in a health checking scenario where it's just looking at, am I getting a valid response or not? These codes are perfectly valid responses. So the health check that we have in NGINX Plus specifically is looking a lot deeper. We can differentiate between different HTTP status codes. We can look at other header information, be that cookies or whatever. We can go so far as to match using regular expressions on body content. That opens up a lot of interesting doors, because that means you can make what I like to call a a health check handshake within the application. So you point your health check routine towards a piece of code. That code does internal sanity checking of the application, checking things like, is the SQL server responding? Is it fast enough? Is the catalog accessible? Then it'll report back to the health check system saying, yeah, I'm open for business, or no, send traffic elsewhere. So yeah, the solution to the issues we've talked about with regards to going to a microservices model can be found in the 3 models we discussed. So the proxy model, the router mesh model, and the fabric model. It's important to note that these are not mutually exclusive. You can combine and mix and match however your architecture will benefit most. So, I believe, yes, there's something special coming up, but before we do that, any questions? Yes, sir. Oh, microphone.
You said you're able to check the body content using regular expression. Now, are you planning to support more high-level techniques like decoding JSON or inspecting XML?
Thanks so much. Very good question. We already do parts of that. With the auth module, we are looking at JWT, for instance. So we can look at elements like that. When it comes to inspecting the body itself and traversing a JSON object, looking for, well, whatever, I can think of a few use cases. I'm not sure if that's on the roadmap. I would have to look into it. I know it's doable, if you want to, by implementing the Lua module, which is a dynamic module. So it's achievable, but you currently have to utilize Lua for that. Good? Cool. Anyone else? Yes, sir.
Thank you. Do you have feature to manage OAuth 2 authorization on OpenID? Or we have to do that by the application?
Excellent question. The answer for OpenID Connect is we support that directly, natively. So that can be taken care of. When it comes to OAuth 2, the answer there too is yes, but with modifications. Because OAuth 2 is no one small thing. It's a million small things that makes a very big thing, right? We do support OAuth 2 in some scenarios. For instance, a token created by Google, we can parse that and consume that. There are some others too. I don't have them off the top of my head, but feel free to contact us and I'll give you a list. Others are coming in as we get them ready. Anybody that claimed they fully support OAuth 2 is likely being slightly dishonest because it's dynamic, it's always growing. There are new federated authenticators coming into OAuth 2 every day. Does that answer the question? Very good. Anyone else? Yes, sir.
How would you compare HA proxy with NGINX Plus?
That question always comes up. The cool answer is I don't. It's a valid question. It's a very, very valid question. We do different things. We do some of the same things, or rather they do some of what we do, the proxying bit. We do a lot more. We do a lot of other things. We have the security module we've talked about here. We have an application server built in, a web server built in. We do load balancing algorithms. They don't yet. I mean, their product is also expanding, and I'm not going to stand here and tell you it's a bad product, because it isn't. It's just we're fitting into different niches, if you will. Does that answer it?